So let's just go back um, on IPv6 extension header. So basically, all of these that we have discussed is just part of an options. One of the options or one of the header or extension header that we can use in IPv6. Later, we will discover that it's actually rarely used for a simple home router. So we have discussed in the previous video how these are the option bits we see in TLB. For example, for jumbo payload, it allows 65 or 64 bytes datagram or jumbo RAM. It is encoded as TLV. Later, we will discover some of the extensions such as routing header and fragment header does not actually follows this TLV structure. So here, this only follows the hop by hop option. Here we have the nodes override normal payload length equals to 0, tunnel encapsulation limit, so it's still TLV. Now, this will be important as a background information on what we will discuss moving forward with regards to routing header, fragment header options, and the um, IP forwarding. So where we are in the IPv6 structure, IPv6 packets are composed of IPv6 base header, 0 or more extension headers. So these are the extension header, could be the hop by hop option, destination option, etc. We will also learn how the hop by hop could be separated from the destination options. So 0 or more extension and the upper layer header, TCP, UDP, ICMP, v6, etc. Among the extension headers, the main header ones in standard order are, in order 1, extension header, hop by hop options, purpose, options, all routers must examine. So they will examine that and check if they can ignore or accept that based on the action bits. Order 2, destination options for routing intermediate destinations, purpose, options for specific nodes. Third, routing header, purpose, controls packet, waypoints. Fourth, fragment header, handles packet fragmentation. Fifth, authentication or ESP, purpose, security. 6. Destination options, final, options for, and host. So far, section 5.3.1 has been explaining the hop by hop options and destination options in detail. That's where all those little TLB option examples, pad1, jumbo, router alert, etc. come in. How the jumbo payload and others connect. Each of these option types is data inside a hop by hop or destination option header, following the TLB type length value structure shown in figure 5.7. So the section order works like this. In section, we have pad 1, 5.3.11, pad 1 or pad n concept, aligns option on an 8-byte boundaries, connection, TLV format examples. 5.2.1.2 jumbo payload concept, hop by hop option to allow greater than 65 kilobytes payload, connection, TLV with type jumbo payload. Section 5.3.1.3 tunnel encapsulation limit concept, limits tunneling depth, connection, TLV used in hop by hop or dest options header. Section 5.3.1.4 router alert concept, alerts routers to inspect this packet. Connection, TLV used in hop by hop options header. Section 5.3.1.5 quick start concept, negotiates data rate. Connection, TLV experimental. Section 5.3.1.6 Calypso concept, security labeling. Connection, TLV private networks. 5.3.1 home address concept, used by mobile IPv6. Connection, TLV, destination options, header after routing header. So all of the 5.3.1x are option types inside an option header, and each follows the same TLV structure. Third, then 5.3.2 routing header will appear in our future videos. Once those examples are done, the text transition to 5.3.2 routing header. This is the next type of IPv6 extension header, not an option inside the previous header but a new header type entirely. So it's not an option inside the TLV structure because it's only for destination and hop-by-hop options. These are for a new header entirely. So the flow look like this conceptually. It actually has a different kind of like TLV structure if you must. So IPv6 base header, then a hop-by-hop option header. It contains options like Jumbo, router alert, etc. Those are where the TLV structure comes in. For the routing header, it's a new header type, its own structure, not TLV. Then we will also discuss in the previous video fragment header and the destination option header we have discussed already. TCP or UDP and ICMP6. That's the connection we're moving up one level in hierarchy. 5.3.1x equal contents inside an option header. 5.3.2 next extension header in the chain. Fourth, conceptual shift from options inside a header to entire new header. The hop-by-hop and destination options header are containers for small TLV based pieces of info, PAD1, Jumbo, etc. The routing header, section 5.3.2, is an entire separate header that controls how a packet moves across multiple destinations. The fragment header, section 5.3.3, is another separate header handling fragmentation and reassembly. So this routing header discuss how the packet moves across routers through the networks, with the base IPv6 base header comes first, just like in the diagram we discussed, and the fragment header is a separate handle or header that handles the fragmentation and reassembly, kind of like the fragmentation in IPv4 as well. So the chapter is stepping through each extension header type in sequence. Option headers, hop-by-hop or destination. For 5.3.2 routing header, 5.3.3 fragment header. Visual overview of connection, IPv6 base header, hop-by-hop options header, PAD1 or PAD-N, Jumbo payload, router alert, quick start. So that's for the hop-by-hop. For routing header, we have type 0, deprecated, type 2 mobile IPv6. We will discuss that in the future video. Fragment header, it also has its own structure. We will also discuss that. Destination option header, final, home address for mobility. We discussed that in the previous video. Upper layer, TCP or UDP, ICMPv6. So we will also glimpse a little bit of this TCP or UDP, because in order to really understand this, you need to understand its upper layer, how it all connects in practice. When a real IPv6 packet is built, first hop-by-hop options header, if needed, carries network level options routers must see. Contains TLV entries like Jumbo payload or router alert. So the hop-by-hop are the network level option that a router must see, and it contains the TLV entries like the Jumbo payload or router alert. Routing header, it's optional, used if sender wants to specify a path. So for the hop-by-hop, it's the router must see it. While for routing header, it's optional, it's used if sender wants to specify a path like mobile IPv6. Fragment header, used only when packet is greater than MTU, sender side fragmentation. Later we will also discuss how this fragmentation work when it comes to its upper layer, and how applications nowadays are able to cut those packet into pieces. The destination options header carries TLV meant only for the final destination, like home address for mobile nodes. Each of these headers is linked by the next header field in the IPv6 base header or the preceding extension header. TLDR, the connection, section 5.3.11 to 5.3.17 describe specific TLV options used inside hop-by-hop or destination options header. Section 5.3.2 routing header and 5.3.3 fragment header describe entirely different extension headers that appear alongside those option headers in the IPv6 packet chain. They're all part of the same family of IPv6 extension headers, just at different levels of the structure. Multiple TLVs inside hop-by-hop or destination options headers. Yes, you're exactly right. So basically, a hop-by-hop options header can carry multiple TLV structures because each option, like router alert, jumbo payload, tunnel encapsulation limit, is its own TLV block. So each router alert, jumbo payload, and tunnel encapsulation actually carries its own TLV. It cannot be in the same TLV at the same time. So example layout, IPv6 base header to hop-by-hop options header, option 1 router alert, we have type equals to 5, len equals to 2, value equals 0x0000. Option 2 jumbo payload, type equals 0xc2, len equals to 4, value equals 000100000. Option 3 pad 1, type equals 0x00. Upper layer like ICMPv6. So after that, you get into the upper layer, ICMPv6 or TCP. Each TLV follows the structure. Field, option type, size in bytes, 1. Description identifies the option. Option data len, size in bytes, 1. Description, length of option data. Field, option data, size in bytes, variable, description, the value itself. So yes, you can combine router alert, jumbo payload, tunnel encapsulation limit, etc. in one hop-by-hop header, each in its own TLV. They can be in the same TLV, but they coexist in sequence inside one options header. Routing header equal new header type, not TLV based. Correct again. The routing header is not like a hop-by-hop or destination options headers. It's a standalone IPv6 extension header with its own unique structure. Field, next header, size in byte, 1. Description, code of next header, i.e. 44 equals to fragment. These are the field of the routing header. Field HDR extension length, size 1 byte. Description, length of routing header. Routing type, size 1 byte. Which kind? It's kind of like the TLV of the hop-by-hop option. Description, which kind, type 0 or type 2, etc. So that type 0 and type 2, we will discuss that in the next video. Segments left, size 1 byte. Number, description, number of intermediate hops left. Field, type specific data. Size variable, description, list of addresses, etc. Used mostly for mobile IPv6 type 2 to route via a home agent. SRv6 segment routing in modern networks replaces MPLS. Most home routers like your Converge ONU router don't generate or process these. Only specialized or backbone routers in ISP cores or more mobile networks do. So mobile IPv6 is to route via a home agent. So most of this or your home router probably won't use this routing header. And the SRv6 segment routing in modern networks only replaces MPLS. Can you have routing header alone? Yes, you can have only routing header and skip hop-by-hop or destination options. IPv6 allows any combination of extension headers like this: IPv6 base header to routing header to fragment header to TCP, so you don't need the hop by hop or destination, or you can have hop by hop alone. There's no requirements to include hop by hop or destination option headers. Most traffic on the internet doesn't use them at all. It's typically IPv6 base header to TCP or UDP or ICMPv6, which headers are commonly used in real-world IPv6 internet traffic. Header, a hop by hop options common. It's rare. Used only for special control, like router alert for MLD. Destination options common. It's only sometimes. Used in mobile IPv6 home address option. Header routing header. Sometimes used for segment routing SRv6 or mobile IPv6. Fragment header, common for large payloads like ICMPv6 or some UDP. AH or ESP, it's used for IPsec tunnels. No extension headers. It's the most common, 99% of traffic. So if you're using Converge on Bulacan, most IPv6 packet your router or kernel sees are just IPv6 base header to TCP or UDP to payload. No hop by hop, no routing header, because ISPs and core routers often drop or ignore packets with exotic extension headers for performance and security reasons. What happens in the kernel, Linux, router, etc.? In the kernel, Linux, router, OS, etc., each header's next header field is used like a linked list pointer. Example packet. IPv6 base header, next header is equals to 0, means hop by hop. So its next header is the hop by hop. Then hop by hop header, next header equals to 43, means routing. So that's its next header field. For routing header, its next header equals to 44, means fragment. Then fragment header, its next header is equals to 58, means ICMPv6. So it's in the transport layer protocol now. So the kernel's IPv6 stack is in net/net/IPv6/IPv6/input.c does something like switch IPv6 HDR to next HDR. Inside it, case next HDR underscore hop, then next IPv6 underscore hop OPTS underscore input SKB, then break, then case next HDR underscore routing, then IPv6 underscore routing underscore input SKB, then break, then case next HDR underscore fragment, then IPv6 underscore fragment underscore input SKB, then next break, case next HDR underscore ICMP, then ICMPv6 underscore RCV argument SKB, then break, then etc. Each extension header handler processes its own portion, then look at its own next header field to pass the packet to the next protocol. This continues until the last one, like ICMPv6, TCP, or UDP. Connection to the fragment header example in 5.14 and 5.15, which we will discuss in the next video. When you read that the next header field contains the value 440x2c, indicating that the fragment header follows the IPv6 header, it means the next header field in the mean IPv6 header equals to 44, which corresponds to fragment header in table 5.5. Then the fragment header has next header equals to 58 ICMPv6. So it means that the next header field in the main IPv6 or the base header is 44, which corresponds to fragment header. That's what we mean by next header field contains the value 44, 0x2c, indicating that the fragment header follows the IPv6 header. Then the fragment header has the next header equals to 58, which means that it is pointing to the ICMPv6 transport layer. Offset equals 181, fragment starts at byte 1448 of original packet. M more fragments equals to 1, not the last fragment, because remember, packet are usually divided, and usually all of this packet has equals to 1 fragments, unless it's the end of the fragment. and the receiver or the transport layer needs to reassemble it. So the packet chain looks like this. IPv6 base header, argument next header equals to 44. Then fragment header, argument next header equals to 58. Then ICMP-v6, echo request payload, part of it. In the kernel, the IPv6 stack uses the that next header link to know, okay, after fragment, expect ICMP-v6. Then this fragment number 2, offset 181 times 8 is equals to 1448 bytes. Store and reassemble when all parts arrive. So offset is 181, it means it has 8 fragments, which when you multiply came into about 1448 bytes. So IP forwarding connection, section 5.4 onwards. This now ties into forwarding. When you your Converge router or your home PC receives the packet, the IP layer looks at the destination IPv6 address. If it's local, deliver to upper layer like ICMP-v6. If it's not local and the node is a router, use the forwarding table to find the next hop via neighbor discovery. So the next header chain is within the packet. How to interpret it? Well, the next hop is outside. Where to send it next? So the next header is within its the packet, not outside the packet, because it's gonna find what is the next extension option. Is it a fragment header, routing header, etc.? Well, the next hop is outside. Where to send it next? So where to send it? What router to send it next? Unlike the individual packets or inside the packet. So your specific context, Converge in Bulacan. In your case, your router receives IPv6 packets from your ISP, Converge backbone. It's unlikely you'll ever see a hop-by-hop or routing header. Converge router are using plain IPv6 plus TCP or UDP most of the time. Fragment headers may appear if large ICMP-v6 messages or path MTU discovery triggers fragmentation. Destination headers are used internally, like if you had mobile IPv6 or tunneling, not in your home usage. You can verify what's seen with bash sudo tcp dump space dash I space n space dash n space IP6. You'll mostly see next header TCP number 6, next header UDP 70, next header ICMP v658, and rarely next header fragment, which is 44. So quick summary of how all this connects. Concept: TLV options, meaning tiny optional fields inside hop by hop or destination headers. Relation, not separate headers. Concept: routing header, meaning entire new IPv6 extension header. Optional, often unused. Fragmentation header, meaning separate header for splitting large packets. Relation, common for ICMP-v6 or tunnels. Next header field points to the next header in chain. Relation, like a linked list pointer. Next hop, forwarding, determines where to send the packet next. Relation based on routing table. Your Converge router likely only process base IPv6 header to TCP or UDP. It doesn't see advanced headers. So how Linux kernel process multiple TLVs, router alert, jumbo payload, etc. When an IPv6 contains a hop-by-hop options header, that header can include multiple TLV options. Each TLV equal type, length, value. The Linux kernel function that handles them is roughly this function. Int IPv6 underscore hop ops underscore input argument struct sk underscore vap asterisk skb. Inside that, struct IPv6 underscore op underscore hdr asterisk hdr equals to struct argument struct IPv6 underscore op underscore hdr asterisk then skb to data. then const unsigned char, opt ptr equal hdr plus 1, then int len equal hdr to hdr len plus 1 less than 3, total length in bytes. Now while opt ptr is less than unsigned char, hdr plus len inside this is u8 opt underscore type equals asterisk opt ptr plus plus semicolon, then if opt underscore type equal ipv6 underscore tlv underscore pad1, then continue, then u8 opt underscore len equal asterisk opt ptr plus plus semicolon, then process underscore option argument opt underscore type comma opt ptr comma opt underscore len semicolon, then opt ptr plus equal opt underscore len semicolon. So that's the algorithm of that. So it iterates through each TLB option one by one, like a while loop reading through a byte array. Each TLV is handled by a case switch, like this switch argument update. Inside this is case IPv6 underscore TLV underscore router underscore alert, then IPv6 underscore router underscore alert argument skb, then break, then case IPv6 underscore TLV underscore jumbo underscore payload, then IPv6 underscore jumbo skb, then break, then case IPv6 underscore TLV underscore tunnel underscore limit, then IPv6 underscore tunnel underscore limit argument skb, then break. So yes, Linux or router kernel goes through all TLVs sequentially, executing each corresponding handle. They're not mutually exclusive, all are parsed. What is ICMPv6? ICMPv6, Internet Control Message Protocol for IPv6, is the control layer of IPv6. It handles NAVOR's discovery, router solicitation or advertisement, ping, echo, request or reply, path, MTU discovery, packet to big messages, multicast listener discovery, MLD. ICMPv6 is essential. IPv6 cannot function without it, unlike IPv4 where ICMP was optional. It sits at the end of the next header chain, like IPv6 base header 2, extension headers if any, then ICMPv6. Third, why ICMPv6 sometimes use fragment header? Good question. ICMPv6 messages are sometimes large, especially packet to big messages. They include part of the offending packet. Router advertisement RA messages with long option list. If the ICMPv6 message is greater than MTU, typically 1 to 80 bytes on IPv6, the sender fragments it using the fragment header. So yes, in real world, routers like Converge fragment large ICMPv6 error messages. Your PC can receive them with fragment header. That's what I meant by fragment header is common for ICMPv6 or tunnels. Fourth, IPsec tunnel, AH or ESP. Yes, AH authentication header and ESP encapsulating security payload are separate extension header types. They are not TLVs inside hub by hub or destination headers. They sit in the chain like this. IPv6 base header to AH, next header equals to ESP, then ESP, next header equals TCP, then TCP payload. They provide AH equal header integrity and authentication, ESP equal encryption and optional authentication, used in VPNs, secure tunnels, and corporate remote access, including call center, work from home, Citrix setups that tunnel traffic to a company network. So yes, what remote workers in the Philippines often use Citrix VPN, IPsec tunnel, is literally using ESP and AH headers in IPv6 or IPv4. Can you have hop by hop without destination options? Yes, totally valid. You can have IPv6 base header to hop by hop to TCP or IPv6 base header to destination options to TCP. You don't have to pair them. They're independent optional headers. What does next header chain mean? Every IPv6 header, even the base header, has a field. So for field, next header, bits 8 bits, description, code indicating what header follow next. Example, header, IPv6 base, next header value 0 means hop by hop options. Example header, hop by hop, The next header value is 43, meaning routing header. Then routing, next header value 44 means fragment header. Then fragment header, next header value 58 means ICMPv6. So yes, it's like a linked list inside the packet. Each header tells the kernel the next piece of the packet is of type X. In Linux kernel code, these are the code switch, next HDR, inside this is case, next HDR underscore HOP, then IPv6 underscore hop ops underscore input, then next HDR equal hop pots, then break, then case, next HDR underscore routing, then IPv6 underscore routing underscore input, then next HDR equal routing, then break, then case, next HDR underscore fragment, then IPv6 frag underscore RCV, then next HDR equals to fragment, then break. So literally uses the HDR to next HDR to follow the chain. Next header versus next hop difference concept, next header where it lives inside the packet, meaning which protocol header comes next, hop by hop, routing, TCP, etc. Next hop in router's forwarding table, meaning which neighbor router to send the packet next to next on its path to destination. So next header equal how to interpret the packet, next hop equal where to send the packet next. Why IPv6 rarely use fragment header? Because IPv6 routers never fragment packets anymore. Only the source host can do it. The minimum MTU on IPv6 is 1 to 80 bytes. Almost all modern networks use path MTU discovery, PMTUD, to avoid fragmentation. Your instinct payload is larger than MTU is right, but IPv6 solved this by requiring applications to use PMTUD instead of fragmentation. So instead of fragmenting, router send back ICMPv6 type 2 packet too big, and the sender shrinks the packet. That's more efficient and secure. Now, is next header equals to 58, offset equals to 181, m equals to 1 a TLV? No, that's not a TLV. That's a fixed format fragment header with fixed field, not type to length value. Field next header bits 8 bits. Description type of next header like 58 equals to ICMPv6. Reserve 8 bits, description unused. Fragment offset bits 13, description position of fragment. M more fragments, bits 1, description more fragments plug. Identification bits 32, description unique ID 4, reassembly. Ano? Ay, wait lang po. Wait lang po. Ano po Sorry about that, guys. Where are we? Oh my god, I think. Oh my god. The one note was did not revert to the previous session. Hmm. So so that's not a TLV. That's a fixed format fragment header with fixed fields, not type or to length to value. So for field, next header bits 8, description type of next header like 58 equal ICMPv6. Field reserve bits 8, description unused. Field fragment offset bits 13, description position fragment. Field more fragments bits 1, description more fragments flag. Field identification bits 32, description unique ID for reassembly. Converged routers IPv6 and neighbor discovery. Yes, your converged 1299 router uses IPv6 internally. It runs neighbor discovery for link layer address resolution like ARP in IPv4, forwarding table FIB for routing decisions, ICMPv6 for router advertisements and reachability probes. So when your laptop connects, it sends router solicitation ICMPv6 type 133. Second, router replies with router advertisement type 134. Third, your laptop configures IPv6 address via SLAAC stateless address auto configuration. Fourth, then neighbor discovery ICMPv6 type 135 over 136 maps MAC to IPv6 address. That's how you reach the internet using IPv6 and D, not ARP. 11. What triggers ICMPv6 or PMTU discovery? Application don't trigger it directly. The kernel IP layer does. Example, you open YouTube, send large packets. If router along the path can't forward because MTU is smaller, say 1280, it sends ICMPv6 packet too big, type 2. Your kernel receives it and reduces the size of future packets to fit. That's path MTU discovery done automatically. VPNs and tunnels in the Philippines, Citrix example. Yes, many BPO or remote employees connect using IPsec or SSL VPNs. IPsec, which is AH/ESP, are IPv6 or IPv4 extension headers. SSL VPNs like Citrix might run over TCP or UDP but still use encapsulation tunnel payload inside another protocol. So when you said, is that what call centers working at home used to connect to Citrix? Exactly, those connections often look like IPv6 to ESP to encrypted tunnel to company LAN, or more common in IPv4 Philippines, ISPs, IPv4 to UDP to SSL VPN to Citrix session. Summary table, hub by hub options belong to extension header, TLV, yes, used for router alerts jumbo payload. Notes kernel iterates TLVs. Concept destination options belong to extension header, TLV, yes, used for mobile IPv6 etc. Notes optional. Concept routing header, extension header, TLV, no. So routing header, it belongs to extension header, TLV, no, used for SRv6 mobile IPv6 nodes, has address list. Concept fragment header belongs to extension header, TLV, no, used for packet fragmentation nodes, fixed fields. Concept AH or ESP belongs to EXT header, TLV, no, used for IPsec tunnels, nodes used in VPNs. Concept ICMPv6 belong to protocol, next header COSA 58, TLV, no, used for control and error handling nodes essential to IPv6. Concept next header belongs to field in every header, TLV, no, used for links to next header nodes like a chain. Concept next hop belongs to routing concept, TLV, no, Used for where to send packet next. Notes used in routing table or F5B. Concept ND neighbor discovery belongs to ICMP v6 function. TLV no. Used for link layer discovery. Notes replaces our first YPath MTU discovery. PMTUD exists. In IPv6, routers are forbidden to fragment packets. Only the sender can. So how can the sender know what the smallest MTU is along the path? That's what PMTUD does. It learns the smallest MTU between you and destination before ever fragmenting. Second, step-by-step example, PMTUD in action. Imagine your laptop converge fiber sending to a game server. Hop laptop to her home router, link 1500. Home router to ISP, link 1492. ISP to game server, link 1280. Step 1. Your laptop sends large IPv6 packets. The kernel assumes MTU equal 1500, sends a 1400 byte UDP datagram. Step 2. Router in ISP sees too big for next hop, 1280 MTU. It drops the packet, does not fragment it, then it sends back an ICMP-v6 packet too big type 2 message. ICMP-v6 type 2, then MTU equals 1280. This is sent back to your laptop. Step 3. Your laptop kernel receives this ICMP-v6 message. It updates its path MTU cache for that destination. Path underscore MTU argument server underscore IP equals to 1280. From now on, all packets to the server are capped at 1280 bytes. Step 4. TCP or UDP layers adopt. TCP automatically reduces its MSS maximum segment size. UDP or raw sockets rely on IP to fragment if allowed or simply send smaller payloads. Result, the sender now avoids fragmentation entirely by adjusting payload size. Third, but most applications send large data. Wouldn't that constantly shrink? Good instinct. But here's the subtlety. Applications like YouTube, games, etc. don't send a huge blob directly at the IP layer. Instead, TCP breaks data into segments that fit MTU. UDP-based apps, games, VoIP, etc. designs packet to already fit often 1-200 bytes max for IPv6. So once the kernel learns the smallest MTU along a path, that value stays cached, minutes to hours. It doesn't keep shrinking. It stabilizes quickly. Example, Linux path cache, IP-6 route get 26 or the MAC address, then MAC address from dev ETH 0 MTU 1280. Fourth, how PMTUD avoids fragmentation in real world. YouTube games memo. App type YouTube video stream. Transfer TCP HTTP over 2. Typical size 1200 to 1400 bytes per segment. Fragmented no. App type online game. Transport UDP. Typical size 200 to 800 bytes. Fragmented no. Emulator memo sync transport UDP. Typical size less than 1000 bytes. Fragmented no. File download TCP. Typical size split in MSS size segments. Fragmented no. In short, modern applications are already MTU aware. That's why they are not fragmented in the first place, because they program their app to be able to follow that MTU aware size. That's why they only have this 1-200 bytes instead of exceeding that normal IPv6 1-80 bytes. So they chunk our segment before hitting the network. So before even getting into this layer 3, they already chunk it. The fragment header structure, not TLV. So this structure, field next header, bits 8 bits, description, type of next header, like 58 equal ICMPv6, field reserve, bits 8, description, unused. Field fragment offset, bits 13, description, position of fragment. Field M, more fragment, bits 1, description, more fragments flag. Field identification, bits 32, description, reassembly ID. Is fixed. So this structure is fixed, not TLV, no type to length to value. So there's no variable graph. It's a static binary format, always 8 bytes long. Visualization. So these are the kind of like the TLV structure of this fragment. So we have next header 8 bits, reserve 8 bits, offset 13 bits, M if it's not the last fragment 1, ID is 32. If M equals to 1, it means more fragments follows, not more fragment headers per se, but more packets with fragment headers sharing the same identification value. 6. Is ICMP v6 always included in IPv6? ICMP v6 is always available, required by IPv6 stack, but it's not always used for user traffic. 2 cases. Traffic type, application data like UDP or TCP. IPv6 plus ICMP v6 use? No. Directly IPv6 to UDP or TCP. Control messages, errors, neighbor discovery, PMTUD. IPv6 plus ICMP v6 use? Yes, IPv6 to ICMP v6. So for caching, that the fragmented size or sending an error, as you can see, we use the ICMP v6, which is always available from IPv6. So your converged IPv6 connection has both ICMP v6 control traffic and UDP or TCP user traffic running side by side. They're not two transport layers, they're two different packet types. 7. How SLAAC looks in kernel and packets. Step 1. Your laptop boots. Kernel calls addr conf underscore dot underscore begin argument dot comma and in 6 addr underscore link local. It creates a link local address FE80 : /64. Step 2. It sends ICMP-v6 router solicitation type 133 ICMP-v6 underscore send. This is how it looks in code. ICMP-v6 underscore send argument dev comma nd underscore router underscore solicit underscore 0 underscore 0. Step 3. Router converge modem replies with router advertisement type 134. Contains prefix 2406 : DA18 : /64 and flags like A equals to 1 autonomous. Step 4. Kernel configures IPv6. In bash, IP-6 addr add 2406, or basically the 2406 : DA18 : ABCD : 123/64 dev ETH0. Step 5. Optional sends neighbor solicitation type 135 for DAD duplicate address detection. 8. How does kernel reduce packet size after PMTUD? When kernel gets packet too big message, first it look up socket route entry, the struct dst underscore entries asterisk dst equals to skb underscore dst argument skb, then dst to ops to update underscore pmtu with an argument dst comma mtu. Then it stores the smaller mtu in the router cache. Then for TCP socket, TCP underscore sk argument sk2 adm vmss equals to mtu minus TCP underscore hdrlen minus IP6 underscore hdrlen. This shrinks segment size automatically. Fourth, for UDP sockets, next send message function call respects the lower MTU or returns EMG size if too large. So no magic, the kernel just remembers the new limit. 9. Why YouTube big packet still fits? Your YouTube video might be megabytes, but that's at application layer. TCP splits it into many segments of 1 to 80 bytes payload each. So you're never sending a huge packet, just a ready stream of MTU size frames. 10. Why ICMP-v6 is called protocol? Next header equals to 58. So IPv6 base header includes next header equal to 58. This simply means the payload after this IPv6 header is an ICMP-v6 message. Like how next header equals to 6 means TCP or 17 means UDP. So value 6 meaning TCP, value 7 UDP, 58 ICMP-v6. That's it, not a transport layer in the sense of apps, but a protocol number. In real-world flow, PMTUD plus fragment plus ICMP-v6, YouTube app, HTTP to TCP segmentation to 1400 byte chunks to the IPv6 layer. It sends packets, MTU equals to 100, then router drops, sends ICMP-v6 packet too big, 1 to 100, then kernel receives ICMP-v6. Next header equals to 58, then path MTU updated to 1 to 80, then future packets limited to 1 to 80. No fragmentation, no packet loss after first adjustment. Summary table, concept, fragment header, type, extension header, variable length, fixed TLV, no. function marks and reassembles fragments. Concept hop by hop header, type extension header, variable length, yes, variable, TLV, yes. Function carries options for all routers, ICMP v6, type, protocol, next header equals to 58, variable length, variable, TLV, no, function control plus error messages, PMTUD, type, mechanism, variable length, nothing, TLV, nothing, function, learns smallest MTU to avoid fragmentation. When MTU drops to 1280, does it slow the game? Not really in practice. The MTU 1500 to 1280 affects how many IP packets are needed to carry the same data. Smaller packets mean slightly more headers per amount of data, but the overall difference is tiny, 1 to 2%. For games or real-time traffic, latency and loss matter much more than MTU. Example overhead, MTU 1500 to payload equals 1460 bytes, TCP or 1472 bytes UDP. For MTU 1280, payload equals to 1240 bytes TCP or 1252 bytes UDP. Overhead, 20 minus 40 bytes over 1500 versus 20 minus 45 over 1280 is equals to 2.6% versus 3.1%. So performance is virtually unchanged. The only noticeable slowdown would happen if PMTUD failed, packets too big, get dropped, and never retransmitted correctly. Second, how TCP and UDP automatically reduce size. TCP is stateful and managed by the kernel. When the kernel receives an ICMPv6 packet too big, type 2, the IPv6 stack updates the path MTU cache. The TCP stack then reduces the MSS maximum segment size for that connection. In Linux source, net/ipv6-route.c plus net/ipv6-tcp_ipv6.c. So when PMTU update is received, DST to ops to update underscore PMTU, argument DST comma new underscore MTU. Then TCP socket reference this, TCP underscore SK, SK2 VMSS equals to new underscore MTU to TCP underscore HDR len dash IP6 underscore HDR len. That's why TCP just adapts automatically. Every future segment sent on that connection uses the smaller ADVMS. So if your PMTU goes 1500 to 1280, ADVMS is equals to 1280 minus 40 IPv6 HDR minus 20 TCP HDR equals to 1220 bytes. Then TCP segmentation does this for you. B. UDP. UDP is stateless. The kernel doesn't fragment by itself unless explicitly allowed. When PMTUD lowers MTU, the kernel stores the smaller value per destination like cache. If a user space program tries to send a bigger UDP programs or a bigger UDP datagram, if fragmentation is disabled, send message returns EMG size. If fragmentation is enabled, kernel splits it into IPv6 fragments. From Linux, net/ipv6/udp.c. If len is greater than DST underscore MTU, argument DST, return -EMG size. So the application itself need to respect MTU. So that will be disabled. Third, how UDP based app design packets less than or equal 1/200 bytes for IPv6. They simply decide to never exceed 1/200 bytes when encoding their protocol data. For example, app type quick used by Chrome or YouTube, max UDP payload 1/200 bytes. Why? To always fit in IPv6 minimum MTU 1280 minus 80 overhead. Games, Valorant, COD, etc. Max UDP payload 500 to 1000 bytes. Why? So one datagram never fragments. App type VoIP/RTP, max UDP payload 200 to 800 bytes. Why? Audio frame sizes naturally small. So the app developers build packet chunking logic like MTU is equals to 1/200, data equals to serialize underscore state underscore update argument players. For chunk in chunk underscore data, argument data, comma MTU, then sock that send to chunk argument chunk, comma server. That's why it just works. The app doesn't hit the MTU limit in the first place. So how path MTU stay cache in Linux? Linux cache MTU per destination in the route cache, argument DST underscore N3. In bash, IP-6 route get 2607 : so this is the MAC, and the next line MAC from : dev ETH0 MTU1280. This is stored in kernel memory, struct DST underscore entry, and then unsigned int underscore path to align underscore MTU, and then unsigned int MTU. And in style, in sysfs bash /proc /net /IPv6 underscore route, then proc /sys /net /IPv6 /conf / MTU. When a PMTUD event occurs, Linux updates that MTU and timestamp it. Entries times out, default 10 minutes to MTU underscore expires unless traffic keeps refreshing it. So the cache ensures that kernel doesn't rediscover PMTU for every packet. So big picture datagram, application, game, quick, it builds less than or equal 1/200 bytes packets, sends via UDP sockets using send message function, then kernel, UDP or IP stack, it checks DST underscore entry, .mtu, if greater than MTU, return EMS gsize, else send via a NIC, then to router, to ISP link. So for router, if it's greater than MTU packets, it drops. If not, it sends ICMP-v6 PTB. Sorry, if it drop, it will send ICMP-v6 PTB. And for kernel ICMP-v6 handler, it updates DST.mtu equals to 1280. Then it logs PMTU cache entry. Then next sends limit to less than or equal 1280 bytes payload. So what happens in high load real world cases like memo or games? First, game starts, kernel assume default MTU 1500. Second, first packet too big, router returns ICMP-v6 packet too big. Third, kernel caches smaller MTU, say 1280. Fourth, game app UDP now sends smaller chunks. Fifth, TCP flows updates chat automatically lower MSS. 6, performance stabilizes, only a few MS lost during discovery, so the network adopts in the first few seconds. Afterward, everything flows at full speed, just with smaller IP frames. Summary table. IPv6 mechanism, PMTU cache. Kernel behavior updates MTU per destination, example code or effect, DST to ops to update underscore PMTU. Layer TCP mechanism adjusts MSS, kernel behavior, TCP underscore SK, argument SK, to ADAVMSS, example code or effect, auto segment smaller. UDP, it checks MTU before send, kernel behavior, returns EMS gsize, example code or effect, app must limit payload. Layer app mechanism chooses less than or equal 1200 bytes. Kernel behavior, manual or quick spec, example coder effect, send to chunk comma server. Where the path MTU cache lives? Yes, it lives in layer 3 network layer below TCP or UDP, especially inside the IPv6 routing subsystem of the kernel, net/IPv6/route.c. It's stored in DST underscore entry, destination entry structure, which belongs to the routing table cache. So TCP and UDP do not have their own PMTU cache. They simply ask layer 3 for the MTU when sending a packet. Structure example simplified: struct DST underscore entry inside unsigned int MTU, then struct DST underscore ops asterisk ops. So the unsigned int MTU is the current path MTU for this route, and the struct DST underscore ops is the function pointers, like update PMTU. When you run IP-6 route get this MAC 2607 etc., you might see 2607 from : dev ETH0 MTU1280. That MTU1280 line is literally read from this DST underscore entry cache. Who sends the PMTU update? That's done by the remote router layer 3 device in the path. When your packet is too big for the next link, the router drops it and sends back an ICMP-v6 packet too big type message. Example, ICMP-v6 type 2 : packet too big, then MTU equals 1280. This ICMP-v6 packet travels back to the source host, your laptop. Your kernel's IPv6 stack receive it like this. Router in path, it sends ICMP-v6 PTB to your Linux IPv6 stack, ICMPv6 underscore receive function, then IP6 underscore SK underscore update underscore PMTU, then DST underscore update underscore PMTU, then updates DST to MTU. How the kernel passes that info upward. Once the kernel updates that path MTU cache, it notifies the transfer layer if necessary. In kernel source simplified //nest/IPv6/ICMP.c, we have void ICMPv6 underscore RCV argument struct SK underscore VAP asterisk SKB. Inside this is if ICMPv6 underscore type equals to ICMPv6 underscore PKT underscore too big, IP6 underscore SK underscore update underscore PMTU argument SKB and FTU. Then for net slash IPv6/IP6 underscore output.c, we have void IP6 underscore SK update PMTU argument struct, and then inside it is struct under DST underscore entry asterisk DST. Common like kind of like the same as the previous code, and that eventually calls net slash IPv6/route.c with the code void DST underscore update underscore PMTU with an argument struct DST underscore entry DST comma U32 MTU. Then if MTU is less than DST to MTU, then DST to MTU equals to MTU. So this updates the cache MTU for that destination. Then TCP layer 4 reacts next time it sends. When TCP next sends data, it does struct DST underscore entry asterisk DST equals to SK underscore DST underscore check argument SK comma 0, then unsigned int MSS equals TCP underscore SK argument SK to ADV MSS. If DST MSS equals to mean MSS comma DST underscore MTU argument DST minus TCP underscore overhead. So TCP always reads the current path MTU from the route cache before building segments. That's why we say PMTU cache in layer 3, but it controls layer 4 segment sizing. The data flow in a nutshell: application sends large packet, then kernel sends via NIC, then router drops too big, sends ICMPv6 packet too big, then kernel receives ICMPv6 PTB, then ICMPv6 underscore receive function to DST underscore update underscore PMTU function, then path MTU cache layer 3 updated to 1280. Then next TP send TCP.output.c reads DST to MTU, set MSS equals to MTU minus headers, then send smaller segments. Big picture layer mapping: layer 7 entity up role sends via socket L4 entity TCP or UDP role segments or sends datagrams. Layer L3 entity IPv6 stack role manages PMTU cache routing. Layer L3 entity ICMPv6 role carries PMTU feedback. Layer L2 entity NIC or driver role actual frame size link MTU. The PMTU cache belongs to L3 IPv6 routing, TCP and UDP. Just query it when sending.